Is our universe truly all there is? Or are we part of something far greater, a multiverse? This question, once relegated to the realm of science fiction, has now entered the halls of serious scientific inquiry. Welcome to our exploration of perhaps the grandest question humanity has ever asked. Are we alone in existence, or is our universe just one bubble in an infinite cosmic ocean? Imagine for a moment that everything we know, every star, every galaxy, every particle of matter from the beginning of time until now, is merely a single page in an endless cosmic library. This is the essence of the multiverse theory, a concept that suggests our universe, vast as it may be, is just one of many universes existing parallel to our own. The journey to this revolutionary idea began in the mundane observations of our own universe. As scientists peered deeper into space with increasingly powerful instruments, they uncovered peculiar patterns and cosmic coincidences that defied simple explanation. The delicate balance of fundamental forces, the precise conditions that allow for the existence of stars, planets, and ultimately life itself, all seemed almost too perfectly calibrated to be mere chance. This cosmic fine-tuning presented a profound puzzle. Either our universe was extraordinarily lucky, or perhaps there was another explanation. What if there are countless universes, each with different physical laws and constants? In such a scenario, our existence in a life-supporting universe becomes not a miracle but a mathematical inevitability. Somewhere in the vast multiverse, conditions would align perfectly for the emergence of stars, planets, and curious beings who gaze upward and wonder about their place in reality. Modern physics has provided several theoretical frameworks that point toward the multiverse's existence. Quantum mechanics reveals a reality far stranger than our everyday experience suggests, a world where particles exist in multiple states simultaneously until observed. String theory, in its attempt to unify all forces of nature, mathematically predicts dimensions beyond the three spatial dimensions we experience, potentially housing other universes. Inflation theory, explaining the early expansion of our universe, suggests this process could create bubble universes, each with its own physical laws. But the multiverse theory isn't just a scientific curiosity, it fundamentally reshapes our understanding of existence itself. If infinite universes exist, then somewhere, every possibility plays out. In some universe, you made different life choices. In another, the laws of physics might be so different that matter as we know it couldn't form. The multiverse challenges our notions of uniqueness and purpose, suggesting that reality is far more vast and varied than we ever imagined. Consider the implications of your daily choices in a multiverse. In this moment, as you listen to these words, uncountable versions of you might be making slightly different decisions, living slightly different lives. Perhaps in one universe, you chose a different career path. In another, you might have taken that risk you always wondered about. The multiverse suggests that all possible versions of your life could be playing out simultaneously across different cosmic domains, each as real as the one you're experiencing now. The concept extends beyond personal choices to the very foundations of physical reality. In some universes, gravity might be stronger or weaker, altering the formation of galaxies and stars. In others, the strong nuclear force might have a different value, making stable atoms impossible. Imagine universes where light travels at different speeds, where time flows differently, or where dimensions beyond our familiar three spatial dimensions are accessible and navigable. This diversity of physical laws across the multiverse offers a solution to one of physics' most perplexing questions. Why do the fundamental constants of our universe seem precisely tuned to allow for complex structures like galaxies, stars, and ultimately life? If infinite universes exist with varying physical laws, then naturally we find ourselves in one of the rare universes where conditions allow for our existence. This is the anthropic principle in action. Not that the universe was designed for us, but that in a vast multiverse, we could only evolve in universes compatible with our existence. The history of this revolutionary idea stretches back further than many realize. While modern physics has given the multiverse concept mathematical rigor, philosophers have contemplated multiple realities for centuries. Ancient Greek philosophers like Democritus proposed the existence of infinite worlds. Medieval thinkers grappled with God's omnipotence and whether it implied the creation of multiple universes. In the 20th century, the concept found new life in both science fiction and theoretical physics, gradually moving from speculation to serious scientific hypothesis. What elevates the multiverse beyond mere speculation is its emergence from established physics rather than pure conjecture. When physicists work through the mathematics of inflation theory, our best explanation for the uniformity and flatness of the observable universe, they find that inflation likely creates not just one universe, but many. Similarly, string theory, in its attempt to reconcile quantum mechanics and general relativity, mathematically predicts a vast landscape of possible universes with different physical laws. The quest to understand the multiverse represents humanity's eternal search for context, our need to situate ourselves within the grandest possible framework of reality. Throughout history, our understanding of the cosmos has continuously expanded. We once believed Earth was the center of all creation. Then we discovered our planet orbits the Sun. Later, we realized our Sun is just one of billions of stars in the Milky Way galaxy. Eventually, we found that our galaxy is one among trillions in the observable universe. The multiverse represents the next conceptual leap, that our entire observable universe might be just one realm in a far greater cosmic structure. This ever-expanding perspective has profound philosophical and spiritual implications. Some find the multiverse concept unsettling, fearing it diminishes human significance or challenges religious narratives. Others find it awe-inspiring, suggesting that reality is far grander and more diverse than we ever imagined. The multiverse doesn't necessarily contradict spiritual beliefs. Indeed, some theologians have embraced it as revealing more of the magnificence of creation. Whatever your perspective, contemplating the multiverse invites a profound humility about humanity's place in existence. The concept also transforms our understanding of possibility and necessity. In traditional cosmology, we might ask why our universe has the specific properties it does. Why this particular arrangement of physical constants rather than another? The multiverse shifts this question. If all possible universes exist, then our universe isn't the result of a single cosmic roll of the dice, but one outcome among countless others. The question becomes not why this universe, but why do we find ourselves in this particular universe? A question the anthropic principle helps address. Critics of the multiverse theory raise valid concerns. Some argue it's unfalsifiable. How can we test for universes beyond our own? Others suggest it violates Occam's razor, the principle that the simplest explanation is usually correct. Yet proponents counter that the multiverse isn't an ad hoc invention, but emerges naturally from our most successful physical theories. And while direct observation of other universes may be impossible, indirect evidence might be detectable in our own universe, particularly in the cosmic microwave background radiation, the afterglow of the Big Bang. As technology advances, our ability to detect subtle clues about the multiverse may improve. Future space telescopes might identify anomalies in the cosmic microwave background that suggest interactions with other universes. Advanced particle accelerators could reveal evidence of extra dimensions predicted by string theory. Theoretical breakthroughs might identify new ways to test these extraordinary ideas. For now, the multiverse remains at the frontier of physics, a concept supported by mathematical models, but awaiting more definitive evidence. Yet, throughout scientific history, concepts once considered untestable, from atoms to black holes, eventually yielded to human ingenuity and technological advancement. The multiverse may follow this pattern, moving from theoretical proposition to established scientific principle as evidence accumulates and methods of investigation improve. As we continue our cosmic journey through this documentary, we will delve deeper into the scientific foundations of the multiverse theory, exploring different models proposed by physicists and the potential evidence supporting each one. We'll examine inflation theory and how it naturally leads to the concept of bubble universes. We'll explore quantum mechanics and the many worlds interpretation that suggests reality branches with every quantum event. We'll investigate string theory and its prediction of a vast landscape of possible universes. To understand the multiverse, we must first understand the boundaries of our own universe, its origin, composition, and the physical laws that govern it. Only by comprehending the one reality we can observe can we begin to theorize about those that might exist beyond our cosmic horizon. To grasp the concept of a multiverse, we must first understand the extraordinary scale and nature of our own universe. What we can see, measure, and study is already so vast that it challenges human comprehension, yet it may be just the beginning of a much larger reality. When we gaze into the night sky, we're actually looking back in time. Light from distant stars and galaxies has journeyed across space for years, decades, even billions of years before reaching our eyes. The most distant objects visible through our most powerful telescopes appear as they were shortly after the universe began, their light having traveled nearly 14 billion years to reach us. This defines what astronomers call our observable universe, a spherical region centered on Earth, with a radius of about 46 billion light-years. You might wonder why the observable universe has a radius of 46 billion light-years when the universe is only about 14 billion years old. The answer lies in cosmic expansion. Space itself has been stretching continuously since the Big Bang, carrying galaxies along with it like raisins in an expanding loaf of bread. This means the most distant galaxies we can see today are now much farther away than when they emitted the light we're just now receiving. Beyond this cosmic horizon lies territory forever hidden from our view. Regions of space whose light, traveling at 186,000 miles per second, hasn't had enough time since the Big Bang to reach us. These regions are part of our universe, but remain invisible to us. We can only deduce their existence through our understanding of cosmic geometry and the uniformity of physical laws. This leads to a profound question. How large is the entire universe beyond our observable limits? Astonishingly, according to most cosmological models, it could be infinite. Even if not truly infinite, observational data suggests it extends far beyond what we can see, potentially hundreds or thousands of times larger than our observable patch. Some estimates suggest the total universe could be at least 10 to the 23rd power times larger than what we can observe. That's a 1 followed by 23 zeros. The most compelling evidence for the vastness of our universe comes from studying its overall shape and composition. Precise measurements of the cosmic microwave background radiation, the oldest light in the universe, released just 380,000 years after the Big Bang, reveal that space is remarkably flat. In geometric terms, this flatness strongly implies an enormous, if not infinite, extent, just as a small section of Earth appears flat despite the planet's overall curvature. This ancient microwave background radiation is one of our most valuable cosmic clues. Discovered accidentally in 1964 by Arno Penzias and Robert Wilson, this faint afterglow permeates the entire sky. It appears as a nearly uniform temperature of 2.7 Kelvin, just above absolute zero, with tiny temperature fluctuations of merely 1 part in 100,000. These minuscule variations represent the seeds that eventually grew into all cosmic structure, the galaxies, stars, and planets that populate our universe today. The striking uniformity of the cosmic microwave background presents one of cosmology's great puzzles. Regions on opposite sides of the observable universe have nearly identical temperatures, yet they're separated by such vast distances that they couldn't have exchanged energy or information since the beginning of time. This horizon problem suggests that these widely separated regions must have been in contact at some point, a paradox that eventually led to the development of inflation theory, which we'll explore in our next segment. The composition of our universe presents another profound mystery. When astronomers calculate the total amount of matter and energy, they find that ordinary matter, the stuff that makes up stars, planets, and people, accounts for less than 5% of the universe's content. About 27% consists of dark matter, an invisible substance detected only through its gravitational influence on visible matter. The remaining 68% is dark energy, an even more mysterious force driving the accelerating expansion of the universe. Dark energy was discovered in 1998, when two independent teams of astronomers found that the universe's expansion isn't slowing down as expected, but actually accelerating. This shocking revelation earned the Nobel Prize in Physics in 2011 and completely transformed our understanding of cosmic destiny. If dark energy continues to dominate, the universe will expand forever, growing increasingly cold and empty as galaxies recede beyond each other's cosmic horizons. This fate, sometimes called the Big Freeze or heat death, represents one possible end for our universe. But in the context of the multiverse, it may be just one of many possible cosmic life cycles. Other universes might experience different fates based on their unique physical properties and energy distributions. Perhaps the most mind-bending aspect of our universe is its beginning, the Big Bang. Contrary to popular understanding, the Big Bang wasn't an explosion in pre-existing space. Rather, it was the beginning of space itself, along with time and all the physical laws that govern reality. According to our best understanding, approximately 13.8 billion years ago, the entire observable universe was compressed into an inconceivably hot, dense state, smaller than a subatomic particle. What happened before the Big Bang? This question may be meaningless within our universe, as time itself began at this moment. However, multiverse theories offer potential answers, suggesting our Big Bang might be just one cosmic event in a much larger reality. Some versions of inflationary theory propose that our universe emerged from a quantum fluctuation in a pre-existing cosmic medium, a scenario that naturally leads to the creation of multiple universes. As we study our universe, we find that its fundamental forces and constants appear remarkably fine-tuned for complexity and life, making complex chemistry impossible. This apparent fine-tuning has led some to invoke divine design, but the multiverse offers an alternative explanation. With enough universes featuring different physical constants, life-supporting universes like ours would naturally occur somewhere. One of the most counterintuitive aspects of our universe is its quantum foundation. At the smallest scales, reality behaves in ways that defy classical intuition. Particles can exist in multiple states simultaneously until measured. Entangled particles can influence each other instantaneously across vast distances. Virtual particles can briefly pop into and out of existence from the quantum vacuum. These quantum phenomena don't just represent curious behaviors at the microscopic scale. They form a fundamental aspect of reality that eventually leads to one of the most compelling arguments for the multiverse, the many worlds interpretation. Our universe also features boundaries of knowledge built into its very structure. Black holes represent regions where gravity is so intense that nothing, not even light, can escape. At the center of each black hole lies a singularity, a point where our current understanding of physics breaks down completely. Similarly, the earliest moments of the Big Bang represent another singularity beyond our theoretical grasp. These limitations hint at deeper layers of reality beyond our current understanding, perhaps pointing toward the existence of a multiverse. As we observe distant galaxies, we notice they're all moving away from us, creates an ultimate horizon to our cosmic view. Galaxies currently beyond our observable universe will forever remain so, their light unable to overcome the expanding space between us. Even more dramatically, galaxies we can see today will eventually disappear from view as they accelerate beyond our cosmic horizon. In the distant future, perhaps 100 billion years from now, observers in our galaxy would see only a handful of nearby galaxies, with the rest of the universe having receded beyond visibility. This eventual isolation of galaxies represents another clue pointing toward the multiverse. If our observable universe is destined to become an increasingly isolated island in a much larger cosmos, perhaps other such islands already exist. Other universes expanding and evolving according to their own physical laws, forever disconnected from our own. The concept of an infinite universe naturally leads us to the multiverse. In an infinite space, with a finite number of possible particle arrangements, every configuration must repeat infinitely. This would mean that somewhere, unimaginably far away, but still within our universe, exact copies of Earth and everyone on it would exist. Yet most physicists find this scenario unsatisfying and problematic. The multiverse theory offers a more elegant alternative, that these other worlds exist not as distant regions in our universe, but as separate universes entirely. As we explore the cosmic microwave background in greater detail, we find subtle patterns that hint at events from the universe's earliest moments. Specific fluctuations in this radiation could potentially bear the imprints of interactions with other universes, or provide evidence of the inflationary process that might naturally generate multiple universes. These whispers from the dawn of time may eventually provide empirical evidence for the multiverse. The path from our understanding of one universe to the concept of many universes flows naturally from established physics. The mathematics that successfully describes our observable universe often points toward larger structures beyond it. This isn't wild speculation, but the result of following our most successful theories to their logical conclusions. Just as discovering that Earth orbits the Sun led to the realization that our solar system is just one among billions in our galaxy, understanding the mechanisms behind our universe's creation suggests it may be one among countless others. If the universe is expanding, what does that mean for the possibility of other universes? The answer lies in understanding cosmic inflation, the extraordinary growth spurt our universe experienced in its first fraction of a second. This theory, developed in the early 1980s, not only solves several puzzling features of our universe, but also provides a natural mechanism for generating multiple universes. Let's explore how this remarkable process works and why it forms the foundation for one of the most compelling versions of the multiverse theory. The most remarkable moment in our universe's history may have been one you've never heard of, a fleeting instant that occurred long before the first stars ignited, before atoms formed, even before the familiar forces of nature differentiated themselves. This moment, known as cosmic inflation, lasted just a fraction of a second, yet fundamentally shaped our entire cosmos, and may have spawned countless others. Imagine the entire observable universe, all 100 billion galaxies with their trillions of stars, compressed to a size smaller than a proton. Then imagine this unimaginably hot, dense point suddenly expanding faster than the speed of light, doubling in size repeatedly in just 10 to the negative 35 seconds. During this brief moment, a region smaller than an atom expanded to astronomical proportions, setting the stage for the more leisurely expansion that continues to this day. This is cosmic inflation, perhaps the most consequential microsecond in cosmic history. Inflation was first proposed in 1980 by physicist Alan Guth while he was investigating problems with the standard Big Bang theory. The original Big Bang model successfully explained many features of our universe, but it left several puzzling questions unanswered. Why is the universe so uniform in temperature across vast distances? Why is space so precisely flat? And why don't we see exotic particles like magnetic monopoles that should have been produced in the early universe? These questions, seemingly unrelated, found a unified solution in the theory of cosmic inflation. To understand inflation, we need to explore the peculiar nature of space itself. In Einstein's theory of general relativity, space is not simply an empty stage where cosmic events play out. It's a dynamic, stretchable fabric that can expand, contract, and bend. More importantly, space can contain energy even in the absence of matter, what physicists call vacuum energy or field energy. During inflation, the early universe was dominated by this form of energy, creating what's called a false vacuum state. False vacuums are inherently unstable, like boulders precariously balanced on mountaintops. When these states decay, they release enormous energy, much like those boulders tumbling down. In the case of cosmic inflation, this decay transformed the vacuum energy into the hot soup of particles that filled the early universe. This transition, known as reheating, marks the end of inflation and the beginning of the more familiar Big Bang expansion. What caused inflation to begin? The answer lies in quantum fluctuations in the early universe. In the extreme conditions just after the universe's birth, quantum effects dominated even at macroscopic scales. Random fluctuations could temporarily create regions with high vacuum energy, triggering exponential expansion. Once inflation began, it was self-reinforcing. The more space expanded, the more energy was available to drive further expansion in a runaway process. The mathematics of inflation reveals something extraordinary. Once it starts, it almost never stops completely everywhere. While inflation ended in our observable universe about 13.8 billion years ago, allowing the familiar processes of the Big Bang to unfold, theoretical models suggest it continues eternally in other regions. This concept, known as eternal inflation, forms the foundation for one version of the multiverse theory. Picture a vast, rapidly inflating sea of spacetime, what physicists call the inflaton field. Within this expanding medium, random quantum processes cause inflation to end in scattered locations, creating bubbles where expansion slows to a more modest pace. Each bubble evolves according to its own initial conditions, potentially developing its own set of physical laws and constants. Our entire observable universe exists inside just one such bubble, while an infinite number of other bubbles, other universes, may populate the greater cosmic landscape. These bubble universes would be genuinely separate from our own, not merely distant regions we can't observe, but distinct cosmic entities with their own spacetime. The space between bubbles continues to inflate at an exponential rate, ensuring that these universes remain forever disconnected. No signal, not even light, could ever cross from one bubble universe to another because the intervening space expands faster than signals can travel. The eternal inflation model makes a profound prediction. Not only do other universes exist, but they're continuously being created. New bubble universes are constantly nucleating in the ever-expanding inflaton field. Some cosmologists estimate that in the time it takes you to hear this sentence, countless new universes have been born into existence. If true, creation isn't a one-time event that happened 14 billion years ago, but an ongoing process happening right now across the greater multiverse. What would these other universes be like? They might differ from ours in ways both subtle and profound. Some might have slightly different values for fundamental constants like the strength of gravity or the mass of the electron. Others might operate under entirely different physical laws or contain different numbers of dimensions. Some could collapse almost instantly, while others might expand forever at varying rates. The diversity of possible universes is limited only by the underlying mathematics of quantum fields, which appears to allow for an almost infinite variety. This brings us to one of the most compelling aspects of inflationary multiverse theory. It naturally explains the apparent fine-tuning of our universe. For decades, physicists have been puzzled by how perfectly calibrated our universe's fundamental constants appear to be for the emergence of complexity and life. Slight changes to these values would create universes where atoms couldn't form, stars couldn't shine, or chemistry couldn't operate. This fine-tuning has sometimes been interpreted as evidence for intelligent design. However, the inflationary multiverse offers a different explanation. If countless universes exist with different physical properties, then naturally some will have conditions suitable for complexity and life, while most won't. We inevitably find ourselves in one of the life-supporting universes because we couldn't exist in the others to make the observation. This reasoning, known as the anthropic principle, transforms an apparent cosmic coincidence into an expected outcome of a diverse multiverse. Inflation also explains several observed features of our universe with remarkable precision. It accounts for the extraordinary flatness of space. Just as inflating a balloon makes its surface appear increasingly flat from the perspective of a tiny observer on the surface, inflation explains why the cosmic microwave background radiation has nearly the same temperature in all directions. These regions were in close contact before inflation exponentially separated them. And it explains the pattern of tiny temperature fluctuations in this radiation, which match exactly what we would expect from quantum fluctuations magnified by inflationary expansion. These successful predictions make inflation the most widely accepted theory of our universe's earliest moments. But how might we find evidence for the broader multiverse it suggests? While we can't directly observe other universes, their existence might leave subtle fingerprints on our own cosmic microwave background. One potential signature would be circular patterns in the microwave background, caused by collisions between our bubble universe and others during the early universe. Another possibility involves gravitational waves, ripples in space-time generated during inflation that could carry information about the greater multiverse structure. Advanced telescopes like the now operational James Webb Space Telescope and future cosmic microwave background missions are searching for these elusive signs. Despite its explanatory power, inflation isn't without its critics. Some physicists argue that the theory has become too flexible, capable of accommodating almost any observation through parameter adjustments. Others point out that the exact mechanism driving inflation remains uncertain, with multiple competing models, and some question whether other universes should be considered scientific entities at all if they forever remain beyond observation. These debates highlight a central tension in modern cosmology, the balance between explanatory power and testability. A good scientific theory should not only explain what we observe, but also make predictions that can be tested. While inflation itself makes testable predictions that have been confirmed, its extension to the multiverse pushes up against the boundaries of what we can verify through direct observation. Yet the history of astronomy offers an important lesson here. Many cosmic entities, once considered beyond observation, from exoplanets to black holes to gravitational waves, eventually yielded to advances in technology and ingenuity. The apparent horizons of scientific observation have repeatedly expanded throughout history. Perhaps evidence for the multiverse, currently at the edge of detectability, will someday become accessible through methods we haven't yet conceived. The mathematics of inflation also reveals something profound about the nature of space-time. During inflation, space expanded faster than the speed of light, which seems to violate Einstein's cosmic speed limit. However, no physical law was broken because it was space itself expanding, not objects moving through space. This distinction highlights how deeply inflation challenges our intuitions about reality. Just as relativity showed that space and time are flexible dimensions rather than rigid backgrounds, inflation reveals that space can undergo extraordinary transformations that defy everyday experience. Another fascinating aspect of inflation concerns the total energy of the universe. As space expands, it creates more vacuum energy, seemingly violating conservation of energy, one of physics' most sacred principles. The resolution to this paradox lies in gravity's negative energy contribution, which precisely balances the positive energy of matter and radiation. In our universe, these energies appear to cancel exactly, resulting in a total energy of zero, a remarkable accounting trick that allowed our entire cosmos to emerge from essentially nothing. This balancing act suggests something profound about the nature of reality and creation. It implies that universes could indeed emerge spontaneously from quantum fluctuations without violating energy conservation. The mathematics of quantum field theory, combined with gravity, not only allows for such creation, but practically demands it. In this view, the emergence of our universe, and potentially countless others, is a natural consequence of fundamental physical laws. Inflation also transforms our understanding of the Big Bang itself. Rather than representing the absolute beginning of everything, The hot Big Bang period we typically reference appears to be just the aftermath of inflation in our local bubble. The true beginning might lie further back, perhaps in the quantum fluctuation that triggered inflation, or in some even earlier process within the greater multiverse structure. Some theoretical models even suggest cycles of inflation, big bangs, and cosmic contractions playing out across the broader multiverse landscape. The concept of eternal inflation emerged naturally from follow-up work by physicists like Andrei Linde, Paul Steinhardt, and Alexander Vilenkin in the 1980s. While developing mathematical models of the inflation process, they discovered that once inflation begins, it naturally becomes self-perpetuating in most regions. Local areas might stop inflating and form bubble universes like our own, but the space between these bubbles continues inflating at an accelerating rate. This creates what Linde called a self-reproducing inflationary universe, what we now recognize as the inflationary multiverse. This model paints a picture of an eternally creative cosmos, a frothing sea of expanding space where new universes continuously emerge like bubbles in boiling water. Each bubble universe undergoes its own evolutionary history, perhaps developing galaxies, stars, planets, and possibly even life forms contemplating their own existence and the nature of reality. From this perspective, cosmic creation isn't a one-time miracle, but an inherent feature of physical law, an ongoing process that has always occurred and may continue forever. One of the most fascinating implications of eternal inflation concerns the ultimate fate of our own universe. Current observations suggest our universe will expand forever, gradually cooling as stars burn out and galaxies recede beyond each other's horizons. Eventually, even matter itself may decay, leaving a cold, dark cosmos of elementary particles separated by vast, empty space. But in the context of eternal inflation, this seemingly bleak fate represents just one chapter in a much grander cosmic story, a story in which creation never ceases and new possibilities eternally emerge. Inflation also provides a framework for understanding space-time on scales far beyond our observable universe. Within our cosmic horizon, space appears to have three dimensions: up-down, left-right, and forward-backward. But string theory, a leading candidate for reconciling quantum mechanics with gravity, suggests additional dimensions might exist, tightly curled up at scales too small to detect. During inflation, these extra dimensions could have expanded differently in different regions, creating bubble universes with varying dimensional structures, some perhaps with additional accessible spatial dimensions. This dimensional diversity could produce universes with dramatically different physics. In a universe with 4 large spatial dimensions, for instance, stable orbits would be impossible. Planets would either spiral into their stars or escape into space. In universes with different dimensional configurations, the fundamental forces might unify differently, producing exotic forms of matter and energy unlike anything in our universe. The kaleidoscope of possibilities becomes even more diverse when considering how quantum fields might settle into different energy states across the multiverse. Many physicists now view inflation not merely as our best theory of cosmic origins, but as a revolutionary paradigm shift in how we understand reality itself. Just as Copernicus showed Earth wasn't the center of the cosmos, and Darwin demonstrated humans evolved from earlier life forms, inflation suggests our entire observable universe may be just one minuscule part of a vastly larger and more diverse multiverse. Each of these conceptual revolutions has expanded our perspective and diminished our cosmic centrality, a humbling but awe-inspiring journey of discovery. If inflation and the resulting multiverse scenario are correct, they highlight something profound about knowledge itself. Science never offers absolute certainty, but progressively builds models that explain observations with increasing accuracy. The multiverse theory represents the current frontier of this process, a framework that elegantly explains features of our universe while generating new questions and research directions. Whether future generations will confirm the multiverse or replace it with an even more comprehensive model remains to be seen, but the quest itself exemplifies humanity's remarkable capacity to explore reality beyond the immediately observable. As we continue exploring cosmic inflation and its implications for the multiverse, we must acknowledge that we've only scratched the surface of this extraordinary theory. The mathematical details and theoretical nuances extend far beyond what we can cover here, but the core concept remains accessible and profound. Our universe appears to be one bubble in a vastly larger cosmic sea, a single chapter in an eternal story of creation playing out across the multiverse. If the universe is expanding through inflation, what does that mean for the possibility of other universes? It means they're not merely possible but probable. Indeed, they're virtually guaranteed by the mathematics of inflationary cosmology. But inflation represents just one path to the multiverse concept. To fully understand the variety of multiverse theories, we must explore other frameworks derived from quantum mechanics, string theory, and even mathematical principles. Each offers a unique perspective on how our universe might relate to a much larger cosmic reality. While inflation theory provides one compelling path to the multiverse concept, it represents just one of several scientific frameworks that point toward the existence of multiple universes. As we explore the frontier of theoretical physics and cosmology, different branches of research have independently arrived at multiverse concepts, each with unique characteristics and implications. This convergence from multiple directions lends credibility to the broader multiverse hypothesis, suggesting it may be more than mere speculation. Let us journey through the main types of multiverses proposed by modern physics, exploring how each arises from established scientific principles. The first and perhaps most straightforward type is what cosmologists call the bubble multiverse, or level 1 multiverse, which emerges directly from inflationary cosmology as we've just explored. In this scenario, our observable universe is just one bubble in an infinitely larger cosmos. Beyond our cosmic horizon lie regions with the same physical laws, but different initial conditions and evolutionary histories. Some regions might be nearly identical to ours, while others might differ dramatically in their arrangement of galaxies, stars, and planets. In an infinite space, with finite possible configurations of matter, every arrangement must eventually repeat, leading to the mind-bending conclusion that perfect copies of our Earth and everyone on it may exist far beyond our observable limits. This concept builds directly on conventional physics, without requiring additional dimensions or altered physical laws. The mathematics of inflation naturally leads to eternal inflation, where space between bubble universes continues expanding exponentially forever. These other bubble universes aren't merely theoretical, they're a straightforward prediction of our best model of cosmic origins. If space extends indefinitely and contains a finite number of possible particle arrangements, then repetition becomes mathematically inevitable, in the same way that a deck of cards shuffled infinitely many times will eventually repeat every possible arrangement. Venturing deeper into theoretical territory, we encounter the quantum multiverse, sometimes called the level 3 multiverse, or many worlds interpretation. This framework emerges not from cosmology, but from the mathematics of quantum mechanics, our most successful theory for describing the behavior of atoms and subatomic particles. Conventional interpretations of quantum mechanics describe particles existing in multiple possible states simultaneously, a phenomenon called superposition, until measured, at which point they collapse into a single state. This collapse has puzzled physicists since the early 20th century, seeming almost magical in its randomness. In 1957, physicist Hugh Everett per second throughout the universe creates new branches. Most of these branches differ only in the position of subatomic particles, but over time, these microscopic differences compound into macroscopic divergences. In some branches, you made different life choices. In others, historical events unfolded differently. The entire cosmic history plays out in every possible way across this vast tree of realities. What makes the quantum multiverse particularly compelling is that it emerges naturally from taking the mathematics of quantum mechanics at face value. without adding the collapse mechanism that other interpretations require. Everett's insight was that allowing reality to branch, rather than collapse, actually simplifies quantum theory by removing the need for an external observer or mysterious collapse process. This mathematical elegance has attracted many physicists despite the mind-bending implications. Moving to even more exotic territory, string theory gives rise to what physicists call the brain-world multiverse or level 2 multiverse. String theory attempts to reconcile quantum mechanics with general relativity by suggesting that the fundamental building blocks of reality aren't point particles, but tiny vibrating strings. These strings require more dimensions than the 3 spatial dimensions we experience, typically proposing 10 or 11 dimensions in total. The extra dimensions are thought to be curled up at scales too small to detect, explaining why we only perceive 3 spatial dimensions in our daily experience. In some versions of string theory, our 3-dimensional universe exists on a brane, short for membrane, floating within a higher dimensional space called the bulk. Other branes may exist within this same higher dimensional space, effectively forming parallel universes that could be separated from ours by distances measured along dimensions we cannot directly perceive. These parallel branes might occasionally interact through gravity, which can propagate through higher dimensions, potentially leaving detectable signatures in our universe. The brain-world scenario offers a particularly dramatic version of the multiverse, where entire universes might exist just a fraction of an inch away from ours, but in a direction we cannot point to because it lies along a dimension we cannot access. Some versions of this theory suggest that what we experience as the Big Bang might have been a collision between our brain and another. Other versions propose that dark matter might be ordinary matter on a parallel brane, visible to us only through gravity's ability to affect multiple branes. Perhaps the most abstract version of the multiverse concept is the mathematical multiverse, sometimes called the level 4 multiverse or ultimate ensemble. Proposed by physicist Max Tegmark, this framework suggests that reality itself is fundamentally mathematical in nature. In this view, every mathematically consistent structure exists as a physical reality somewhere in the multiverse. Our universe exists because its underlying mathematical structure is consistent. It contains no logical contradictions that would prevent its existence. This perspective radically expands the multiverse concept to include not just universes with different physical constants or histories, but universes operating under entirely different mathematical frameworks. Some might have different numbers of dimensions, different conceptions of time, or even different logical systems altogether. The mathematical multiverse encompasses all logically possible realities, with our universe representing just one mathematical structure among infinitely many. While the mathematical multiverse might seem too abstract to qualify as a scientific theory, Tegmark argues that it actually represents the ultimate application of Occam's razor, the principle that the simplest explanation is usually correct. Rather than asking why our particular mathematical structure exists while others don't, the mathematical multiverse proposes that all consistent structures exist, removing the need for any special explanation of our universe's specific properties. Another variant of multiverse theory emerges from cyclical models of the universe, which propose that our universe undergoes repeated cycles of expansion and contraction. In these models, each cycle could produce a universe with different properties. After a universe completes its expansion and collapses back to a singularity, it rebounds in a new Big Bang with potentially different physical constants. This creates a temporal sequence of universes, each giving birth to the next through cosmic death and rebirth. One particularly elegant cyclical model comes from physicists Paul Steinhardt and Neil Turok, who proposed the ekpyrotic universe scenario. In their model, our universe exists on a brane that periodically collides with a parallel brane. Each collision creates the hot, dense conditions we associate with the Big Bang, generating a new cycle of cosmic evolution. This model potentially explains cosmic features without requiring inflation, offering an alternative path to understanding our universe's origins. Simulated universes represent yet another category of potential multiverse. The rapidly increasing power of computing suggests that eventually, civilizations might create simulations sophisticated enough to contain conscious entities unaware of their simulated nature. If this is possible, then for every base reality, countless simulated realities could exist, suggesting that any randomly selected consciousness is statistically more likely to exist in a simulation than in base reality. This simulation hypothesis, popularized by philosopher Nick Bostrom, doesn't require exotic physics or higher dimensions, just sufficient computing power and the desire to create simulations. If our universe is a simulation, then the real universe might operate under entirely different physical laws. The computer running our simulation might exist in a universe with 5 spatial dimensions, different fundamental particles, or completely alien concepts of space and time. These diverse multiverse concepts share a common theme. They all emerge naturally from attempts to solve existing problems in physics and cosmology. None were invented specifically to propose multiple universes. Rather, the multiverse emerged as a consequence of following established scientific principles to their logical conclusions. This convergence from multiple theoretical directions lends credibility to the broader concept, suggesting the multiverse may be more than mere speculation. How might these different types of multiverses relate to each other? Rather than being competing theories, they might represent different aspects or levels of the same overarching reality. Cosmologist Max Tegmark has proposed a hierarchical classification system that integrates these various concepts. Level 1, the bubble multiverse. Regions beyond our cosmic horizon with the same physical laws but different initial conditions. Level 2, the inflationary multiverse. Other bubble universes with potentially different physical constants, created through eternal inflation. Level 3, the quantum multiverse, branching realities created by quantum events, as described by the many worlds interpretation. Level 4, the mathematical multiverse, all mathematically consistent structures existing as physical realities. In this hierarchical view, each level encompasses and expands upon the previous levels, creating an increasingly comprehensive framework for understanding the totality of existence. Critics of multiverse theories often raise valid concerns about testability and falsifiability, traditional hallmarks of scientific theories. If other universes exist beyond our observable horizon, how can we ever confirm their existence through experiment or observation? This challenge has led some philosophers of science to question whether multiverse theories qualify as scientific at all, or whether they represent metaphysical speculation dressed in mathematical language. Proponents counter that indirect evidence can support multiverse theories, even if direct observation remains impossible. The predictive success of theories that naturally lead to the multiverse, like inflation, lends credibility to their multiverse implications. Moreover, the history of science shows that theoretical entities once considered unobservable, from atoms to black holes, eventually yielded to advancing technology and ingenuity. Some potential tests for various multiverse theories are already being developed. Bubble universe collisions might leave detectable patterns in the cosmic microwave background radiation. Quantum mechanics experiments might reveal evidence for or against the many worlds interpretation. Modifications to gravity at very small scales might support or contradict certain string theory models that predict parallel branes. The concept of multiple universes transforms our understanding of possibility and necessity. In traditional cosmology with a single universe, we might ask why our universe has the specific properties it does. The multiverse shifts this question. If all possible universes exist in some form, then our universe isn't the result of a single cosmic roll of the dice, but one realization among countless others. The question becomes not why this universe, but why do we find ourselves in this particular universe? A question the anthropic principle helps address. This anthropic reasoning suggests that of all possible universes, we necessarily find ourselves in one compatible with our existence. If the electromagnetic force were significantly stronger or weaker, atoms couldn't form stable structures, and life as we know it couldn't exist. In a multiverse with varying physical constants, intelligent observers will always find themselves in universes whose properties allow for their existence, not because these universes were designed for life, but because life could only evolve to ask the question in such universes. The multiverse concept also challenges traditional notions of design and purpose in the cosmos. Throughout history, the apparent fine-tuning of our universe for life has suggested to many a cosmic designer who calibrated physical constants precisely to allow for our existence. The multiverse offers an alternative explanation. With enough universes featuring different physical properties, life-supporting universes would naturally occur somewhere without requiring design or purpose. Yet far from diminishing the wonder of existence, the multiverse concept can enhance it. The possibility that our universe is one among countless others, each with different properties and evolutionary histories, makes our existence all the more remarkable. In the words of physicist Brian Greene, if the multiverse idea is correct, then the historic mission of physics to explain all of nature from first principles is hopeless. While this may seem disappointing, I'd argue that there's a thrill in learning that the diversity of nature's richness may be vastly greater than we had ever imagined. As we contemplate these various multiverse models, from bubble universes to quantum branches, from parallel brains to mathematical structures, we're reminded that science continually expands our conception of reality beyond what previous generations could imagine. The multiverse represents the frontier of this expansion, challenging us to consider the possibility that our universe, vast as it seems, may be just one expression of an even grander cosmic tapestry. But is inflation the only theory suggesting a multiverse? As we've seen, definitely not. Multiple paths in modern physics and cosmology independently lead toward multiverse concepts. This convergence from different theoretical directions suggests we may be glimpsing aspects of a deeper reality, one in which our universe represents just one manifestation of the cosmos's creative potential. If the multiverse exists, how could we detect it? This question brings us to the frontiers of observational cosmology and the ingenious methods scientists are developing to search for evidence of realities beyond our cosmic horizon. If other universes exist beyond our own, how could we possibly detect them? This question strikes at the heart of whether the multiverse qualifies as a scientific theory or merely an intriguing philosophical speculation. By definition, other universes exist outside our observable reality, beyond what we can directly measure or witness. Yet despite this fundamental challenge, scientists have developed ingenious approaches that might reveal indirect evidence of these parallel realities. Let's explore the potential clues that could hint at a cosmos far vaster and more diverse than our observable universe. The most promising avenue for detecting evidence of other universes comes from studying the cosmic microwave background radiation, the oldest light in the universe, released about 380,000 years after the Big Bang, when the universe first became transparent. This ancient radiation permeates the entire sky and has been mapped with extraordinary precision by satellites like WMAP and Planck. Hidden within its subtle temperature variations and polarization patterns may lie telltale signs of cosmic events that could only be explained by the existence of other universes. One specific signature scientists search for is evidence of bubble universe collisions. In the eternal inflation model, our universe is one bubble among countless others in a rapidly expanding cosmic medium. Occasionally, these bubbles might collide, creating characteristic circular patterns in the cosmic microwave background, cosmic bruises left behind when our universe bumped into another. These collisions would appear as disc-shaped regions with slightly different temperature distributions than surrounding areas. Several research teams have scanned cosmic microwave background data for these distinctive patterns, though no definitive evidence has yet been found. Another potential signature involves what cosmologists call large-scale anomalies in the cosmic microwave background. According to the standard cosmological model, temperature fluctuations should be randomly distributed across the sky, following specific statistical patterns. However, observations have revealed several unexpected features, including a strange alignment of temperature patterns across vast distances, sometimes called the axis of evil, and an unusual cold spot in the southern sky that's larger and cooler than expected from random fluctuations. While these anomalies might have conventional explanations, some theorists suggest they could be imprints left by interactions with other universes or remnants of our universe's birth from a larger multiverse structure. Gravitational waves, ripples in the fabric of space-time first directly detected in 2015, offer another potential window into the multiverse. These waves are generated by violent cosmic events, such as black hole collisions, and propagate throughout the universe. Some theories suggest that gravitational waves might also be produced by events in the early universe related to inflation or by interactions with other universes. Advanced gravitational wave detectors might someday detect distinctive patterns that could only be explained by multiverse dynamics. Particularly significant would be the detection of primordial gravitational waves, ripples generated during the inflationary period of the early universe. These waves would carry information about inflation itself, potentially confirming aspects of inflationary theory that naturally lead to the multiverse concept. Several experiments, including specialized telescopes in Antarctica and Chile, are searching for the subtle polarization signatures these primordial gravitational waves would leave in the cosmic microwave background. The distribution of galaxies throughout space could also provide clues about the multiverse. The way matter clusters on the largest scales follows patterns predicted by quantum fluctuations in the early universe. If our universe were influenced by other universes during its formative stages, or if it represents one region in a larger cosmic structure, subtle deviations from expected distribution patterns might be detectable. Future galaxy surveys mapping billions of galaxies across unprecedented volumes of space could reveal these telltale statistical anomalies. Perhaps the most counterintuitive potential evidence for the multiverse comes from quantum mechanics itself. The behavior of quantum systems, particularly the phenomenon of quantum entanglement, where particles maintain instantaneous connections regardless of distance, has led some physicists to suggest that we may already be observing multiverse effects. According to certain interpretations, quantum phenomena might represent interactions between parallel realities in the quantum multiverse. Increasingly sophisticated quantum experiments might eventually distinguish between various interpretations, potentially providing indirect evidence for the many worlds framework. Laboratory experiments from searching for extra dimensions could also support multiverse theories based on string theory. If our universe exists on a brane within higher dimensional space, gravity might leak into these extra dimensions at very small scales, causing slight deviations from the expected inverse square law. Several experiments have tested gravity's behavior at microscopic distances, searching for these deviations. While no evidence for extra dimensions has yet been found, more sensitive future experiments could potentially detect them, lending support to brane-world multiverse models. Some scientists have proposed that dark matter, the mysterious substance that provides gravitational attraction but doesn't interact with light, might actually be evidence of another universe's gravitational influence on our own. In certain brane-world scenarios, gravity can propagate between parallel branes, allowing matter in one universe to gravitationally affect another without any other form of interaction. This could potentially explain why we detect dark matter only through its gravitational effects. Future observations of dark matter distribution might reveal patterns consistent with this cross-brane influence. The apparent fine-tuning of our universe's fundamental constants provides another indirect argument for the multiverse. Our universe appears remarkably calibrated for complexity and life. If the strengths of fundamental forces or the masses of elementary particles were slightly different, atoms wouldn't form, stars wouldn't shine, and life couldn't exist. This fine-tuning has two possible explanations. Either our universe was somehow designed with these precise values, or there exist many universes with different values, and we naturally find ourselves in one of the rare universes compatible with our existence. The second explanation, an application of the anthropic principle within a multiverse framework, becomes increasingly compelling if direct evidence for other universes emerges. While the search for empirical evidence continues, the theoretical case for the multiverse has strengthened through developments in fundamental physics. String theory, once hoped to produce a unique description of our universe, instead revealed a vast landscape of possible universes, perhaps 10 to the power of 500 different possible configurations, each representing a universe with different physical properties. This unexpected theoretical discovery, emerging from one of physics' most sophisticated mathematical frameworks, hasn't proven the multiverse exists, but has made it increasingly difficult to explain why only one possible universe configuration should be realized in nature. Similarly, developments in inflation theory have reinforced its prediction of multiple universes. When physicists analyze the mathematics of how inflation would work, they consistently find that once inflation begins, it should continue eternally in some regions while ending in others, naturally generating bubble universes with different properties. This prediction isn't an add-on to inflation, but emerges directly from its core mathematics. Since inflation successfully explains observed features of our universe, its prediction of a multiverse carries significant theoretical weight. The scientific community remains divided on whether these theoretical arguments and potential observational signatures are sufficient to establish the multiverse as a scientific theory rather than a speculative hypothesis. Critics point to the challenge of falsifiability, a cornerstone of the scientific method. If a theory can accommodate any possible observation by appealing to variations across an unobservable multiverse, has it abandoned predictive power? Proponents counter that indirect evidence can still support multiverse theories, and that requiring direct observation of other universes imposes an unreasonable standard that would have prevented many historical scientific advances. This debate reflects a broader tension in modern cosmology between explanatory power and testability. Some of our most elegant and comprehensive theories make predictions that strain the limits of what we can observe. Yet the history of science offers numerous examples of theoretical entities once considered beyond observation, from atoms to black holes to the expansion of the universe itself, that eventually yielded to advancing technology and human ingenuity. As we assess the case for the multiverse, we should remember that throughout scientific history, the cosmos has repeatedly proven larger, more diverse, and more extraordinary than our initial conceptions. Humans once believed Earth was the center of a single, small universe. We now know our planet orbits an ordinary star in a galaxy containing hundreds of billions of stars, and our galaxy is one among trillions in the observable universe. Each expansion of our cosmic understanding seemed radical when first proposed, yet later became the established scientific consensus. Perhaps the multiverse represents the next horizon in this ongoing expansion of our cosmic perspective. The philosophical divide among scientists on this question, between multiverse believers and skeptics, reflects broader tensions in how we approach the limits of knowledge. Some emphasize theoretical elegance and explanatory power, finding in the multiverse a comprehensive framework that naturally accounts for our universe's specific features. Others prioritize empirical verification, remaining cautious about theories that strain the boundaries of what we can observe. Both perspectives contribute valuably to scientific progress, with the creative tension between them driving new discoveries and methodological innovations. In the end, the question of whether the multiverse exists may be decided not by philosophical preference, but by the gradual accumulation of empirical evidence. As our observational tools improve and our theoretical understanding deepens, we may discover subtle signatures that can only be explained by the existence of other universes, or we may develop alternative frameworks that explain our universe's features without requiring cosmic multiplicity. Either outcome would advance our understanding of reality exemplifying science's remarkable capacity to explore questions at the very boundaries of human knowledge. But if the multiverse is real, what would that mean for our understanding? Touching on our most fundamental concepts of existence, possibility, identity, and purpose. Let's explore how the multiverse reshapes our understanding of reality at its most basic level. Perhaps the most immediate philosophical shift involves our concept of possibility. In a single universe framework, we naturally ask why our universe has the specific properties it does. Why particular physical constants? Why these specific laws of physics? Why this exact evolutionary history? The multiverse transforms these questions entirely. If all possible universe configurations exist somewhere in the multiverse, then our universe isn't the result of a singular cosmic roll of the dice, but one outcome among countless others that all exist simultaneously. The question becomes not why this universe, but why do we find ourselves in this particular universe? A question the anthropic principle addresses. This shift fundamentally alters how we think about cosmic fine-tuning. Our universe appears remarkably calibrated for complexity. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the nuclear forces were slightly weaker, no elements heavier than hydrogen would form. This fine-tuning has two possible explanations. Either our universe was somehow designed with these precise values, or there exist many universes with different values, and we naturally find ourselves in one of the rare universes compatible with our existence. The multiverse makes the second explanation not merely plausible, but expected. The implications for the concept of cosmic design are profound. Throughout history, the apparent fine-tuning of our universe for life has suggested to many a cosmic designer who calibrated physical constants precisely to allow for our existence. The multiverse offers an alternative explanation. With enough universes featuring different physical properties, life-supporting universes would naturally occur somewhere without requiring design. This doesn't disprove the existence of a creator, but does provide a naturalistic explanation for what otherwise seems like an extraordinary cosmic coincidence. Even more mind-bending are the implications of quantum multiverse theories, particularly the many worlds interpretation. If reality branches with every quantum event, creating parallel realities for each possible outcome, then every decision you've ever made, and every decision you didn't make, plays out somewhere in the quantum multiverse. In some branch of reality, you chose a different career path. In another, you took that risk you always wondered about. In countless others, small differences in quantum events led to dramatically different life trajectories, or even prevented your existence entirely. This quantum multiplicity challenges our most basic notions of identity and choice. If every possible version of you exists somewhere in the multiverse, what does that mean for your sense of self? Are all these alternate versions equally you? The quantum multiverse suggests that identity isn't singular, but branches endlessly, with each version of you experiencing a different slice of the total multiverse. Your subjective experience remains linear and singular. You only experience one branch, but the totality of you spans countless realities. Similarly, the multiverse transforms our understanding of possibility and necessity. Philosophers have long distinguished between what's merely possible and what's actually real. The multiverse dissolves this distinction. If every possibility is realized somewhere in the multiverse, then all possibilities are actualized. Nothing is merely possible. Everything that can happen does happen in some universe. This doesn't mean everything happens in our universe. The laws of physics still constrain what's possible within each universe, but across the entire multiverse, all logically consistent possibilities would manifest somewhere. This has profound implications for how we understand counterfactuals, statements about what might have happened if things had gone differently. In standard thinking, when we say, if I had taken that job, I might be living in Chicago now, we're speculating about an unrealized possibility. In a quantum multiverse framework, that possibility is realized. There is a branch of reality where you did take that job and are living in Chicago. Counterfactuals aren't merely hypotheticals, but descriptions of actual realities in other branches of the multiverse. The multiverse also transforms our understanding of infinity and uniqueness. In an infinite multiverse with finite possible configurations, every arrangement must repeat infinitely many times. This means there would be infinitely many universes virtually identical to ours, with duplicates of Earth and everyone on it living out nearly identical lives. There would also be infinitely many universes with slight variations. Perhaps Earth formed 1,000,000 years earlier, or dinosaurs never went extinct, or human history took a dramatically different course due to a single change decision at a pivotal moment. This infinite repetition creates what philosophers call the identity problem. If there are infinite copies of you scattered throughout the multiverse, all with slightly different experiences, but the same fundamental makeup and memories up to some point, which one is the real you? The multiverse suggests that uniqueness itself may be an illusion, that what we consider our singular identity is actually one instance of a pattern repeated across the cosmic landscape. The multiverse also reshapes our conception of death and finitude. In the many worlds interpretation, every quantum possibility branches reality, including those affecting life and death. This suggests that for any potentially fatal event, there always exists at least one branch of reality where you survive, while you subjectively only experience the branches where you continue to exist. The implication is that subjective experience might continue indefinitely along at least some path through the quantum multiverse, a concept sometimes called quantum immortality. This isn't to suggest practical immortality. In our experience branch of reality, biological death remains inevitable, but it does raise profound questions about the nature of consciousness and its relationship to the physical structures that support it across the branching realities of a quantum multiverse. If consciousness is what it feels like to be a physical system processing information, how does that experience navigate the branching pathways of a quantum reality? The multiverse concept also transforms how we might understand the emergence of life and consciousness. In a single universe, the appearance of life, particularly intelligent life, seems remarkably fortunate, requiring a precise sequence of evolutionary developments over billions of years. In a multiverse with varying physical constants and infinite evolutionary histories, the emergence of life and consciousness becomes not merely possible, but inevitable in those universes with suitable conditions. Life isn't a cosmic fluke, but a natural outcome of the multiverse's vast creative potential. This perspective connects to what cosmologists call the observer selection effect, the principle that we can only find ourselves in a universe compatible with our existence. No matter how rare life-supporting universes might be in the greater multiverse, conscious observers will always find themselves in one of those rare universes, because that's the only place they could exist to make the observation. This isn't circular reasoning, but a necessary consideration when interpreting our cosmic circumstances. The multiverse also offers a new perspective on the question of cosmic purpose. In instances of the cosmos becoming aware of itself, our ability to contemplate the multiverse, to develop theories about realities beyond our direct experience, becomes not a cosmic accident, but a remarkable manifestation of complexity emerging from fundamental physical processes. The multiverse also transforms how we might think about simulated realities. If technological civilizations eventually develop the capacity to create detailed simulations containing conscious entities, as some futurists predict, then simulated universes might vastly outnumber base reality universes in the total multiverse. This raises the statistical possibility that our own reality might be a simulation created by beings in another universe. The multiverse and simulation hypotheses aren't mutually exclusive, but potentially complementary. Simulated universes could represent one mechanism by which the multiverse's creative potential manifests. If our universe were a simulation, it would raise profound questions about its relationship to the base reality in which the simulation runs. The physical laws we observe would reflect parameters set by the simulators rather than fundamental features of base reality. The constants that appear fine-tuned for life might be deliberately calibrated by the simulators to allow for our emergence. Our entire conception of reality would necessarily shift to accommodate this nested relationship between simulated and simulating universes. The multiverse also offers a new framework for understanding coincidence and pattern. In a single universe, remarkable coincidences might seem to demand explanation. Why should unrelated events align in meaningful ways? In an infinite multiverse, every possible configuration of events occurs somewhere, including those featuring remarkable coincidences. Observers in universes with striking coincidences might mistakenly attribute special meaning to what are actually random alignments that were bound to happen somewhere in the multiverse. This doesn't mean all patterns are meaningless. Within each universe, cause and effect still operate according to physical laws, but it does suggest caution in interpreting coincidences as evidence of cosmic design or purpose. In an infinite multiverse, even the most improbable alignments of events would occur in some universes, and observers in those universes might naturally but mistakenly see significance in what are actually random configurations that had to happen somewhere. The multiverse concept also transforms how we might understand free will and determinism. In classical physics, the universe appeared fully deterministic. If you knew the position and momentum of every particle, you could, in principle, predict the entire future. Quantum mechanics introduced fundamental uncertainty, potentially creating space for free will. The quantum multiverse, however, suggests a different perspective. All possible choices are realized somewhere in the branching realities, yet each individual consciousness experiences making specific choices along its particular world line. This creates what philosophers call compatibilism, a reconciliation between determinism and free will. While the total multiverse might contain all possible decision pathways, your subjective experience involves actually making choices that determine which branch of reality you experience next. Your decisions still matter for your subjective journey through the multiverse, even if all possible decisions are realized across different branches. The multiverse also reshapes how we might understand cosmic justice or fairness. In a single universe, the distribution of fortune and suffering often appears arbitrary and unjust. Why do some experience great happiness while others endure terrible suffering, often due to circumstances beyond their control? In an infinite multiverse, every possible distribution of fortune occurs somewhere. Each conscious entity experiences one path through this landscape of possibilities, but across the multiverse, all possible experiences are realized. This doesn't solve the problem of suffering in our experienced reality, but does place it in a different cosmic context. The apparent injustice of our universe isn't a flaw in cosmic design, but a reflection of our location in the multiverse landscape. In other branches of reality, different distributions of fortune and suffering play out. This cosmic perspective doesn't diminish the importance of pursuing justice and reducing suffering in our experienced universe, but does reframe the philosophical problem of evil and suffering. The multiverse concept also transforms our understanding of the connection between mathematics and physical reality. Traditionally, it seemed remarkable that mathematics, a seemingly human invention, so perfectly describes the physical world. The mathematical multiverse hypothesis suggests a different relationship. Perhaps mathematical structures don't just describe reality, but constitute it. Every logically consistent mathematical structure corresponds to a physical reality somewhere in the multiverse. This would explain the unreasonable effectiveness of mathematics, noted by physicist Eugene Wigner. Mathematics describes reality so well because reality is fundamentally mathematical. This perspective also addresses why certain mathematical equations, like those of quantum mechanics or general relativity, describe our physical world while others don't. In the mathematical multiverse, all consistent mathematical structures are physically realized somewhere, but we naturally find ourselves in a universe described by equations that allow for our existence. Other mathematical structures correspond to universes with different physical laws, perhaps too simple to allow complexity or too chaotic to allow stable structures. Beyond these philosophical implications, the multiverse concept challenges us to reconsider our cosmic significance. Throughout history, humans have alternatively seen themselves as the center of creation or as insignificant specks in an indifferent cosmos. The multiverse offers a more nuanced perspective. While we're not the center or purpose of cosmic creation, our capacity for consciousness and understanding represents something remarkable. We are the means by which a tiny corner of the multiverse has become aware of itself and begun to comprehend the greater reality beyond its immediate experience. This reframing of cosmic significance echoes what philosopher Daniel Dennett calls the view from nowhere, the capacity to step outside our immediate perspective and consider reality from an objective standpoint. Our ability to conceive of the multiverse, to develop mathematical models of realities we can't directly observe, represents a remarkable transcendence of our limited viewpoint. Through science and philosophy, we reach beyond our cosmic horizon toward a more comprehensive understanding of existence itself. If we are living in one of many universes, every choice you've ever faced has played out differently somewhere in the quantum multiverse. For every decision point in your life, every possible outcome exists in some branch of reality. In some universe, you pursued that childhood dream you abandoned. In another, you told that person how you really felt. In countless others, tiny quantum fluctuations led to completely different life circumstances or prevented your existence entirely. Yet your subjective experience remains that of a single consciousness moving through time, making choices that matter for your particular journey through the cosmic landscape. This perspective can be both liberating and challenging. On one hand, it suggests that the weight of possibility doesn't rest entirely on your shoulders. All possibilities are realized somewhere. On the other hand, it emphasizes that your experienced reality, the one branch you subjectively navigate, is shaped by your choices. The road not taken exists somewhere in the multiverse, but not in your experienced reality. Your decisions still determine which branch of the possible you actually experience. The effect of these cosmic concepts on our psychological understanding can be profound. The multiverse offers a framework for integrating regret, choice, determinism, and possibility into a coherent picture of existence. Your life represents one path through a vast landscape of possibility, a unique journey through the infinite potential of the multiverse. What gives that journey meaning is space in the greater multiverse, revealing how the specific properties of our cosmic home fit within the vast landscape of cosmic possibility. Our universe harbors two profound mysteries that dominate its composition and destiny: dark matter and dark energy. These invisible components make up approximately 95% of our universe's content, yet we understand almost nothing about their fundamental nature. Even more intriguing is how these mysterious substances might vary across different universes, potentially creating vastly different cosmic environments and evolutionary histories. By exploring dark matter and dark energy in the context of the multiverse, we gain new insights into how these enigmatic forces might connect to the greater cosmic plurality. Let's begin with dark matter, the invisible substance that provides gravitational attraction but doesn't interact with light. When astronomers observe galaxies, they find that visible matter, stars, gas, and dust, accounts for only about 15% of the gravitational force needed to explain how galaxies rotate. The remaining 85% comes from an invisible substance that betrays its presence only through gravitational effects. This dark matter forms vast halos around galaxies, providing the gravitational scaffolding that shapes cosmic structure. Despite decades of research, the fundamental nature of dark matter remains elusive. Leading candidates include exotic particles like weakly interacting massive particles, WIMPs, or axions that interact only through gravity and the weak nuclear force. Alternative theories suggest modifications to our understanding of gravity itself rather than new types of matter. Whatever its nature, dark matter played a crucial role in cosmic evolution, creating the gravitational wells that allowed normal matter to coalesce into the galaxies and stars we see today. In a multiverse context, dark matter becomes even more intriguing. Different universes might contain varying amounts of dark matter relative to normal matter, creating dramatically different cosmic environments. In universes with less dark matter, galaxies would form more slowly or not at all, potentially preventing the emergence of stars and planets. In universes with more dark matter, cosmic structures might become too dense, with frequent stellar collisions preventing the stable planetary environments needed for life. Our universe's ratio of dark matter to normal matter, roughly 5:1, appears calibrated to allow the formation of stable galaxies, stars, and planets. This specific ratio permitted hydrogen and helium from the Big Bang to gradually coalesce into the cosmic structures we observe today. If this ratio were significantly different, the cosmic evolution necessary for complexity and life might not have occurred. In the context of the multiverse, our universe's dark matter abundance might represent one value in a vast spectrum of possibilities, with most configurations hostile to complexity. Even more mysterious than dark matter is dark energy, the enigmatic force driving the accelerating expansion of our universe. Discovered in 1998 through observations of distant supernovae, dark energy acts like anti-gravity, pushing space itself apart at an ever-increasing rate. This discovery transformed our understanding of cosmic destiny. Rather than eventually slowing down or collapsing, our universe appears destined to expand forever, growing increasingly cold and empty as galaxies recede beyond each other's cosmic horizons. The nature of dark energy represents one of the greatest puzzles in modern physics. The simplest explanation identifies it with the energy of the vacuum itself, the baseline energy present in empty space due to quantum fluctuations. However, theoretical calculations of vacuum energy yield values enormously larger than observed dark energy, a discrepancy that represents the most extreme mismatch between theory and observation in all of science, off by a factor of 10 to the power of 120. This cosmological constant problem, why vacuum energy appears so precisely tuned to a tiny but non-zero value, finds a natural explanation in the multiverse framework. If different universes feature different values of vacuum energy, then most universes would have values too large to allow for complex structures. In universes with large positive vacuum energy, space would expand too rapidly for galaxies to form. In universes with large negative vacuum energy, space would quickly collapse back in a big crunch before stars could form. Only universes with vacuum energy in a narrow range would allow for the cosmic evolution necessary for complexity and observers. Our universe's dark energy value appears extraordinarily fine-tuned, just strong enough to accelerate expansion in the universe's later stages, but not so strong as to prevent the formation of galaxies, stars, and planets in its earlier epochs. This remarkable calibration, often cited as evidence for cosmic design, emerges naturally from multiverse models combined with anthropic reasoning in an ensemble of universes with varying dark energy values. Observers like us could only evolve in the rare universes with values in the narrow, life-permitting range. String theory provides a theoretical foundation for this multiverse explanation of dark energy. The mathematics of string theory reveals a vast landscape of possible vacuum states, perhaps 10 to the power of 500 different configurations, each corresponding to a universe with different physical properties, including different values of dark energy. While this landscape doesn't prove the multiverse exists, it provides a mathematical framework that naturally accommodates the observed fine-tuning of our universe's dark energy. The interplay between dark matter and dark energy across the multiverse creates a fascinating spectrum of possible cosmic evolutions. In some universes, dark energy might dominate from the beginning, preventing any significant structure formation. In others, dark energy might be absent, allowing gravity to eventually halt expansion and collapse the universe. In still others, dark energy might emerge later than in our universe, allowing more time for cosmic structures to develop before acceleration begins to tear them apart. Our specific cosmic history with dark matter dominating the early universe to build cosmic structures, followed by dark energy's emergence about 5 billion years ago to begin accelerating expansion, represents just one pathway through this landscape of possibilities. This particular sequence created a cosmic environment conducive to complexity and life during a specific window of time. Other universes might feature different sequences, creating cosmic environments that remain sterile or that develop forms of complexity vastly different from what we observe. The study of dark matter and dark energy might also provide observational clues about the multiverse itself. If our universe has interacted with other universes, through bubble collisions in the early universe or through gravitational effects across branes in higher dimensions, these interactions might leave distinctive signatures in the distribution of dark matter or in the behavior of dark energy. Anomalies in dark matter distribution or unexpected variations in dark energy across cosmic time could potentially serve as evidence for these inter-universal interactions. Some theories propose that dark matter itself might be a manifestation of matter in parallel universes. In certain brane-world scenarios, gravity can propagate between parallel branes, allowing matter in one universe to gravitationally affect another. Without energy, different destinies might unfold. In universes where dark energy strengthens over time, a scenario called phantom energy, acceleration would eventually become so extreme that it would tear apart galaxies, solar systems, planets, and ultimately atoms themselves in a big rip. In universes where dark energy weakens and becomes negative, expansion would eventually reverse, leading to a big crunch, where all matter collapses back to a singularity. And in universes with perfectly balanced energy configurations, a cyclic pattern might emerge, with periods of expansion followed by contraction in an endless cosmic heartbeat. The study of dark matter and dark energy across possible universes represents one of the most promising frontiers for multiverse evidence. Advanced telescopes and detectors may soon reveal subtle patterns in cosmic structure or unexpected behaviors in cosmic expansion that could support or contradict various multiverse models. While direct observation of other universes remains beyond our current capabilities, these indirect clues could strengthen the case for cosmic plurality. The mysterious nature of dark matter and dark energy, components that dominate our universe yet remain fundamentally enigmatic, reminds us of how much remains to be discovered about cosmic reality. If the history of astronomy offers any lesson, it's that the universe repeatedly proves larger, more diverse, and more extraordinary than our initial conceptions. Perhaps dark matter and dark energy, in their very mysteriousness, are pointing toward an even grander cosmic picture, one in which our universe represents just one expression of reality's creative potential. If other universes exist, could we ever travel between them? This question brings us to the frontier, where theoretical physics meets science fiction, the possibility of inter-universal travel or communication. While current physics suggests profound barriers to such cosmic journeying, the theoretical concepts of wormholes and quantum entanglement offer intriguing, if speculative, avenues for thinking about connections between universes in the greater multiverse. If other universes exist beyond our own, could we ever hope to reach them? This question captures our imagination, blending cutting-edge theoretical physics with our ancient desire to explore beyond known frontiers. While contemporary physics suggests profound barriers to such cosmic journeying, several theoretical concepts offer intriguing, if highly speculative, avenues for contemplating connections between universes in the greater multiverse. Let's venture into this frontier, where science approaches science fiction, exploring the theoretical possibilities and fundamental challenges of inter-universal travel. The most immediate challenge to inter-universal travel stems from the very nature of the multiverse. In most models, other universes exist outside our space-time continuum entirely, not merely at great distances within our own universe. The bubble universes of eternal inflation exist in regions where space continues to expand exponentially, forever driving them beyond our cosmic horizon. The parallel branches of the quantum multiverse exist in separate realms of Hilbert space, not in our physical space. The brain worlds of string theory inhabit higher dimensions inaccessible to our direct experience. This fundamental separation makes conventional travel between universes, in the sense of continuous motion from one point to another, seemingly impossible by definition. Yet theoretical physics offers several concepts that might potentially bridge these cosmic gaps, beginning with Einstein-Rosen bridges, more commonly known as wormholes. First proposed in 1935, wormholes represent theoretical tunnels through space-time that could connect distant regions of our universe or potentially different universes altogether. These cosmic shortcuts theoretically fold space-time, creating passages that bypass the normally required travel through regular space. While Einstein's equations permit wormholes mathematically, they present enormous practical challenges. Natural wormholes, if they exist at all, would likely be microscopic, unstable, and located near extreme gravitational environments like black holes. More problematically, traversable wormholes would require exotic matter with negative energy density to remain open, a substance that may not exist in sufficient quantities in nature. Without this exotic matter, wormholes would collapse instantly when anything attempted to pass through them. Some theoretical physicists, including Kip Thorne and his colleagues, have explored whether advanced civilizations might someday create artificial wormholes large and stable enough for actual travel. This would require not only mastering the manipulation of negative energy, but developing technology capable of engineering the very fabric of space-time itself. Such capabilities would represent a level of technological development far beyond anything currently imaginable, and would likely require harnessing the energy resources of an entire galaxy. Another theoretical approach involves quantum entanglement, the phenomenon Einstein famously called spooky action at a distance. When particles become entangled, their properties become correlated in ways that transcend spatial separation. Some theoretical physicists have speculated that this quantum connection might potentially transcend not just space, but the boundaries between universes in the quantum multiverse. This quantum approach to inter-universal connection aligns most naturally with the many-worlds interpretation of quantum mechanics, where reality branches with every quantum event. Since these branches all stem from a common origin, primordial entanglements might theoretically persist across them. If so, information, though perhaps not matter or energy, might potentially be exchanged between parallel quantum realities through carefully managed entanglement experiments. However, extracting meaningful information through such quantum connections faces profound practical challenges. Quantum measurement collapses entanglement, allowing only one bit of correlated information to be extracted per entangled pair. Furthermore, the no-communication theorem in quantum mechanics prohibits using entanglement alone for faster-than-light or cross-universal communication. While future developments in quantum information theory might identify loopholes in these limitations, current understanding suggests extremely limited potential for inter-universal connection. String theory's brain world scenario presents another conceptual framework for thinking about inter-universal travel. In this model, our universe exists on a three-dimensional membrane, or brain, floating in a higher dimensional space called the bulk. Other universes might exist on parallel branes, potentially separated from ours by distances measured in dimensions we cannot directly perceive or access. Some versions of brain theory suggest that certain particles, particularly gravitons, the theoretical particles that carry the gravitational force, might be able to travel between branes through the bulk. This could explain why gravity appears weaker than the other fundamental forces, because some of its influence leaks into other dimensions. If gravitons can travel between branes, then perhaps other particles or forces could be engineered to make the same journey, potentially enabling some form of cross-brain signaling or detection. However, actually moving macroscopic objects or people between branes would require overcoming enormous energy barriers. The forces that bind matter to our brain are incredibly strong, strong enough to prevent us from perceiving or directly interacting with extra dimensions in our daily experience. Breaking these bonds would likely require energy concentrations comparable to those in the earliest moments of the Big Bang, conditions we can barely approach even in our most powerful particle accelerators. The cosmic bubble universes proposed by eternal inflation theory present perhaps the most formidable inter-universe or even request transfer to different simulated realities. However, this would require first convincing the simulators that such communication or transfer is warranted, a task that would likely require demonstrating levels of technology or understanding that signal readiness for broader multiverse awareness. Beyond these theoretical frameworks, some physicists have explored whether advanced civilizations might create baby universes in laboratory settings. Theoretical calculations suggest that with sufficient energy concentration, perhaps approaching what could be harnessed from an entire star, it might be possible to create conditions similar to those that generated our universe. Communication. The barriers appear not merely technological, but built into the fundamental structure of reality itself. The very frameworks that lead us to consider the multiverse's existence simultaneously suggest its components remain causally disconnected and mutually inaccessible. Yet the history of science offers important perspective here. Throughout human development, we've repeatedly encountered seemingly insurmountable barriers that later yielded to new understanding and technology. Ancient civilizations could not imagine crossing oceans. Pre-modern humans could not conceive of flying through the air. The boundaries of the possible have repeatedly expanded beyond what previous generations could imagine. This pattern suggests humility in declaring anything forever impossible, especially regarding civilizations that might exist millions or billions of years in our future. If intelligent life persists and continues technological development for timescales comparable to geological or astronomical epochs, capabilities might emerge that our current science can no more anticipate than Stone Age humans could have anticipated space travel. Nevertheless, inter-universal travel represents a qualitatively different challenge than previous frontiers. It's not merely a matter of overcoming practical limitations like distance or energy requirements, but of crossing boundaries potentially woven into reality's fundamental structure. The gaps between universes in most multiverse models aren't in space but beyond space entirely. Not locations we lack the means to reach, but domains we lack the dimensional access to approach. For now, our exploration of the multiverse remains primarily theoretical and observational, developing mathematical models, searching for indirect evidence in our cosmic microwave background, and contemplating the philosophical implications of cosmic plurality. This intellectual exploration represents its own remarkable journey, one in which human minds, evolved on a small planet orbiting an ordinary star, reach beyond their cosmic horizon toward a vision of reality far grander and more diverse than our ancestors could have imagined. While the idea of inter-universal travel is fascinating, what ethical and philosophical questions does it raise? If we somehow develop the ability to interact with other universes, what responsibilities would that entail? Would we be cosmic visitors, observers, colonizers, or creators? These profound questions about our potential relationship with the greater multiverse speak to our deepest values and our vision of humanity's place in the cosmic order. The multiverse concept doesn't merely challenge our scientific understanding, it fundamentally transforms how we conceive of existence itself. Throughout human history, most belief systems have positioned humanity as uniquely significant in a single, purposefully created cosmos. But what happens to these deeply held convictions when faced with the possibility of infinite universes, each with its own evolutionary history and perhaps its own conscious beings? Consider how the multiverse reshapes our sense of cosmic uniqueness. Many religious traditions teach that our universe was specifically created for humanity, that the cosmos was intentionally designed with us in mind. The fine-tuning of physical constants seems to support this view, as the precise calibration of forces appears almost miraculous, yet the multiverse offers an alternative explanation that requires no divine intervention. With infinite universes featuring different physical properties, life-supporting universes like ours would naturally occur somewhere, and conscious beings would only evolve in those rare universes capable of supporting complexity. This shift from special creation to statistical inevitability doesn't necessarily contradict religious belief. Some theologians have embraced the multiverse concept, suggesting it reveals even greater divine creativity, not just one universe, but a cosmic abundance beyond imagination. In this view, God becomes not the architect of a single reality, but the creator of infinite possibility itself. The multiverse doesn't eliminate the divine, but potentially expands our conception of divine creative power. Others find the multiverse deeply unsettling to traditional faith. If our universe is just one random variation among countless others, does that diminish its significance? Does it reduce the miracle of existence to mere probability? These questions touch our deepest spiritual intuitions about meaning and purpose in the cosmos. Some fear that in expanding our conception of reality, we might lose the intimate connection between humanity and creation that gives life its spiritual dimension. The concept of infinite copies of ourselves existing across the multiverse presents perhaps the most profound psychological challenge. Imagine universes where you made different choices, where you pursued that abandoned dream, took that untaken risk, or chose the other path at every crossroads in your life. In some versions of the multiverse theory, particularly the many worlds interpretation of quantum mechanics, every possible version of you exists somewhere, living out every potential life path you could have taken. This infinite multiplication of self challenges our most basic sense of identity and uniqueness. Are all these that underpin many spiritual traditions? Eastern philosophical traditions may find the multiverse more compatible with their worldviews. Buddhist conceptions of reality as fundamentally interconnected and illusory align with the quantum concepts that resonate with modern multiverse theories. The ancient Hindu text Brahma Vaivarta Purana even describes thousands of universes emerging from a cosmic ocean, an image strikingly similar to bubble universes in eternal inflation theory. Western religious traditions have typically emphasized a single created cosmos, but even here, there are conceptual bridges to multiverse thinking. Medieval Jewish, Christian, and Islamic philosophers grappled with questions about God's omnipotence. Could an all-powerful deity create multiple worlds? The 12th century Jewish philosopher Maimonides argued that divine omnipotence must extend beyond our single reality. Thomas Aquinas, while favoring a single universe, acknowledged that God could create many worlds if he chose. These theological explorations show that even traditional monotheism contains seeds of multiverse thinking. Perhaps most profoundly, the multiverse transforms our understanding of possibility and actuality. In traditional thought, there's a clear distinction between what actually happens and what merely could have happened. The multiverse dissolves this boundary. Everything that could happen does happen somewhere. Your unrealized possibilities aren't just hypothetical alternatives, but realities playing out in other branches of existence. This reshapes concepts of choice, regret, and potential that lie at the heart of both philosophical inquiry and spiritual reflection. The psychological impact of multiverse thinking can be both liberating and disturbing. Some find comfort in the idea that somewhere every possibility is explored, that nothing is truly lost because all potentials are realized somewhere in the cosmic plurality. Others experience existential vertigo at the thought of infinite copies of themselves, living out every possible variation of their lives. This tension between liberation and anxiety reflects our deeper struggle to situate ourselves within a reality far vaster and more diverse than our intuitions prepare us to comprehend. The multiverse also transforms how we might understand suffering and justice. In a single universe, the uneven distribution of fortune and misfortune can seem arbitrary and unjust. Why do some experience great happiness while others endure terrible suffering? The multiverse doesn't solve this problem for our experienced reality, but does place it in a different cosmic context. Across the multiverse, every possible distribution of fortune and suffering occurs somewhere. This cosmic perspective doesn't diminish the importance of pursuing justice in our experienced universe, but does reframe the philosophical problem of evil and suffering. Some physicists who embrace the multiverse concept have experienced profound shifts in their spiritual outlook. As physicist Brian Greene reflects, "When I think about the multiverse, I feel both larger and smaller at the same time. Larger because I'm connected to an enormous, possibly infinite reality that encompasses not just what is, but all that could be. Smaller because my own existence becomes one tiny branch on an endlessly bifurcating tree of cosmic possibility. This paradoxical expansion and humbling of the self echoes mystical experiences described across spiritual traditions. The multiverse also challenges us to reconsider what we mean by creation itself. In many religious traditions, creation is depicted as a singular, intentional act, God speaking the world into existence or shaping it according to divine plan. In multiverse cosmology, creation becomes an ongoing, perhaps eternal process, with new universes constantly bubbling into existence through natural physical processes. This shift from creation as singular event to creation as inherent cosmic fertility asks us to reconsider what we mean by the sacred and the divine. Philosophers have long contemplated whether our universe is unique or one among many. The ancient Greek atomist Democritus proposed countless worlds forming and dissolving in an infinite void. Renaissance philosopher Giordano Bruno suggested infinite worlds might orbit other stars, a heretical view that contributed to his execution by the Inquisition. The German philosopher Gottfried Leibniz proposed that God would create the best of all possible worlds, a concept that takes on new meaning if all possible worlds exist somewhere in the multiverse. Whatever our personal beliefs, the multiverse invites a profound humility about humanity's place in existence. Throughout history, our understanding of the cosmos has continuously expanded, from Earth as the center of creation, to our planet as one world orbiting one star in one galaxy, to our entire observable universe as potentially one bubble in a vastly greater cosmic structure. Each expansion of perspective has challenged human exceptionalism while simultaneously revealing the extraordinary feat of consciousness that allows us to comprehend realities far beyond our immediate experience. If you're finding these concepts mind-bending or even spiritually challenging, you're not alone. The multiverse represents the frontier of human understanding, pushing against the limits of what our minds, evolved on the savannah to track predators and find food, can comprehend. Yet there's something remarkable in our ability to even conceive of these possibilities, to develop the mathematics that points toward realities beyond our direct experience. Perhaps our capacity for wonder is itself a cosmic gift, allowing a tiny corner of the multiverse to become conscious of its own grandeur. As we continue our cosmic journey, we'll explore how future scientific advancements might bring us closer to evidence of the multiverse, and how these discoveries might transform our understanding of reality itself. The search for other universes represents more than scientific curiosity. It's humanity's latest chapter in the ancient quest to understand our place in the cosmos, a quest that has always interwoven scientific, philosophical, and spiritual dimensions in the tapestry of human knowledge. What does the future hold for our quest to understand the multiverse? While we may never directly observe another universe, advancing technology offers promising avenues to search for indirect evidence that could transform speculation into established science. The journey ahead is already unfolding through increasingly sophisticated tools and techniques that probe the boundaries of our observable reality. The James Webb Space Telescope, humanity's most powerful eye on the cosmos, represents our best hope for detecting subtle clues about the early universe that might support multiverse theories. With its unprecedented infrared sensitivity, Webb can peer further back in cosmic time than any previous instrument, capturing light from the earliest galaxies and stars. By studying the cosmic dawn, That moment when the first luminous objects emerged from primordial darkness, Webb might detect patterns or anomalies that only make sense in a multiverse framework. Particularly revealing would be precise measurements of the cosmic infrared background, which could potentially show signatures of interactions with other bubble universes during our universe's infancy. Future cosmic microwave background missions will build on the groundbreaking work of satellites like Planck and WMAP, mapping the mind temperature fluctuations in this ancient radiation with ever greater precision. Scientists are particularly interested in detecting what's called B-mode polarization in the cosmic microwave background, a subtle pattern that would provide smoking gun evidence for primordial gravitational waves generated during inflation. Since inflation naturally leads to multiverse scenarios in many theoretical frameworks, confirming these gravitational wave patterns would significantly strengthen the case for cosmic plurality. The next generation of gravitational wave observatories promises to revolutionize our understanding of the cosmos. Current detectors like LIGO and Virgo have already achieved the remarkable feat of detecting ripples in space-time from colliding black holes and neutron stars. The Higgs boson in 2012 represented a triumph for the standard model of particle physics, but many questions remain unanswered. Next-generation particle accelerators, such as proposed circular colliders with circumferences of 100 kilometers or more, could probe energies approaching those of the early universe, potentially revealing evidence for supersymmetry, extra dimensions, or other phenomena predicted by theories that naturally lead to multiverse scenarios. Particularly intriguing is the search for microscopic black holes. Some versions of string theory suggest that if extra dimensions exist, gravity might be much stronger at very small scales, allowing particle collisions to create tiny black holes. Detecting these exotic objects would provide compelling evidence for extra dimensions, a key component of certain multiverse models. While the Large Hadron Collider has found no evidence for such phenomena yet, future accelerators with significantly higher energies might push into territory where such discoveries become possible. Quantum computing represents another frontier technology that might indirectly contribute to multiverse exploration. As these systems grow in power and sophistication, they may allow scientists to simulate complex quantum systems that help test predictions of the many worlds interpretation. While such simulations wouldn't prove the existence of parallel quantum realities, they could demonstrate that the mathematics leading to the many worlds framework accurately describes quantum behavior in increasingly complex scenarios, lending credibility to its multiverse implications. Advanced telescopes are already searching for cosmic anomalies that might hint at a multiverse. The Simons Observatory in Chile's Atacama Desert, for example, is designed specifically to study the cosmic microwave background with unprecedented precision, looking for subtle patterns that might reveal interactions with other universes. Future projects like the Cosmic Microwave Background Stage 4 experiment will push these observations to theoretical limits, potentially detecting the faintest imprints from our universe's birth that could support or contradict various multiverse models. The study of dark energy, that mysterious force accelerating our universe's expansion, offers another promising avenue for multiverse evidence. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will conduct the most precise measurements yet of cosmic acceleration. If dark energy's strength varies over time or across different regions of space in unexpected ways, it could indicate interactions with other universes or support theories that naturally lead to multiverse scenarios. These precise measurements might help determine whether our universe's dark energy value truly represents an extraordinary cosmic coincidence or an expected outcome in a diverse multiverse. Some theoretical physicists are exploring whether quantum experiments might someday provide evidence for the quantum multiverse. While we can't directly observe other branches of reality in the many worlds interpretation, increasingly sophisticated quantum interference experiments might reveal subtle deviations from expected patterns that could only be explained through interactions between parallel quantum realities. These experiments push at the boundaries of what's possible, requiring control of quantum systems with unprecedented precision while isolating them from environmental interference. Mathematical advances could also transform our understanding of the multiverse. As theoretical physicists develop more refined models of eternal inflation, quantum gravity, and string theory, they continuously refine their predictions about what a multiverse would look like and what traces it might leave in our observable reality. Sometimes the most significant breakthroughs come not from new observations, but from deeper mathematical insights that reveal connections between seemingly unrelated phenomena, perhaps showing how certain features of our universe make sense only as part of a larger multiverse structure. Artificial intelligence and advanced data analysis are revolutionizing how we search for subtle patterns in cosmological data. Machine learning algorithms can detect correlations and anomalies in vast datasets that might escape human notice, potentially revealing the faint fingerprints of other universes imprinted on our cosmic microwave background or galaxy distribution. As these techniques grow more sophisticated, they might identify multiverse signatures that conventional analysis would miss, transforming how we extract information from our cosmic observations. The power of these technological advances lies not just in individual capabilities, but in their combination. When observations from next-generation telescopes are combined with results from particle accelerators, gravitational wave detectors, and quantum experiments, patterns might emerge that point convincingly toward a multiverse framework. Science advances most significantly when multiple independent lines of evidence converge on the same conclusion, and the future may bring exactly this kind of convergence for multiverse theories. Throughout scientific history, theories once considered untestable have repeatedly yielded to human ingenuity and technological advancement. Continental drift was once dismissed as speculative because no one could imagine how to test it, until the discovery of seafloor spreading and magnetic striping on the ocean floor provided compelling evidence. Black holes were considered mathematical curiosities for decades before astronomical observations confirmed their reality. The apparent horizons of scientific testability have expanded repeatedly throughout history, and the multiverse may follow this pattern. Some scientists are developing what they call multiverse predictions, phenomena that would be expected in our universe if it exists within a greater multiverse structure. For example, certain patterns of cosmic inflation would be more likely in a multiverse scenario than in a single universe model. By identifying and testing such predictions, scientists hope to build the case for the multiverse through accumulating circumstantial evidence. Even if direct observation remains impossible, the ultimate test for any scientific theory isn't direct observation of every predicted entity, but successful explanation and prediction of observable phenomena. Atomic theory was accepted long before individual atoms could be directly observed, because it successfully explained and predicted chemical reactions. Similarly, the multiverse theory might eventually be accepted not because we can see other universes, but because it provides the most comprehensive and mathematically elegant explanation for features of our observable reality. What makes this quest for multiverse evidence so remarkable is that it represents humanity's attempt to understand reality beyond what we can directly perceive, to use mathematics, logic, and indirect observation to glimpse a cosmic structure far grander than our senses can detect. Throughout history, human understanding has continuously expanded beyond immediate perception, from the microscopic world of atoms and cells to the macroscopic realm of galaxies and black holes. The multiverse represents the next conceptual leap in this progression, challenging us to comprehend a reality in which our entire observable universe might be just one realm in a far greater cosmic structure. As our tools and methods advance, we may discover that reality is even stranger and more diverse than current multiverse theories suggest. The history of physics has repeatedly shown that new discoveries often reveal reality to be more exotic than our previous conceptions. When quantum mechanics emerged in the early 20th century, it revealed a subatomic realm that defied classical intuition. Perhaps our current multiverse models will similarly be superseded by even more comprehensive frameworks as our understanding deepens. The search for the multiverse ultimately represents science at its most ambitious, reaching beyond what we can directly observe to understand the largest possible context for our existence. Whether future evidence strengthens or weakens the case for the multiverse, the journey itself exemplifies human curiosity and our remarkable capacity to comprehend realities far beyond our evolutionary origins. Our ability to develop these theories and design experiments to test them represents something profound about consciousness itself, that a tiny corner of the cosmos has evolved the capacity to contemplate its own origins and place within a potentially vast cosmic plurality. As our cosmic journeys comes to a close, we return to the profound question that began our exploration. Are we alone in existence, or is our universe just one bubble in an infinite cosmic ocean? While definitive answers remain elusive, the very journey of contemplation transforms how we see our place in reality. The multiverse represents both the frontier of modern physics and the latest chapter in humanity's eternal quest to understand our cosmic context. Throughout history, our conception of reality has continuously expanded, from a flat Earth at the center of creation to our planet orbiting one star among billions, to our galaxy as one among trillions. Perhaps the multiverse represents the next horizon in this ongoing expansion of perspective, not a final answer, but another step in our evolving understanding. Whether other universes exist beyond our cosmic horizon may never be conclusively proven, yet the mathematics that successfully describes our observable reality consistently points toward larger structures beyond it. This convergence from multiple theoretical directions suggests we may be glimpsing aspects of a deeper truth, one in which our universe represents just one expression of reality's creative potential. The multiverse will follow this pattern, with future generations finding evidence that transforms today's theoretical frameworks into established science. If the multiverse exists, it transforms how we understand existence itself. Our universe, vast as it is with hundreds of billions of galaxies stretching across billions of light years, would be just one realm in a cosmos of unimaginable diversity for existence. Whether we live in the only universe or minds, in that quest for understanding, we discover not just the nature of reality, but something profound about ourselves, beings capable of contemplating infinity from our tiny corner of existence.